Okay. So good morning, everyone. I'm Leo. I'm the founder and research lead of MigaLabs. I have been collaborating with the Ethereum Foundation for about 8 years, I think now. We have done multiple research projects, and what I'm going to present here today is one of those research projects in the context of data availability sampling. So this is more or less the outline of my talk. I'm gonna explain what is the motivation behind this work. Then I'm gonna introduce, DNEP, which was when we started to having blobs in Ethereum. Then I'm gonna talk about what the state of the art is today. And then I will present what we expect to have for Fusaka, so which is the next fork, and what we are trying to introduce for the next fork, which is Glamsterdam, in terms of data availability sampling and a sharded mempool. And finally, I will conclude. So for the motivation, what we want to do here, and all this research is based on, is under the context of scaling. What we want is to scale Ethereum. An easy way to summarize scaling would be, in the context of a blockchain, is to do more transactions per second. That's kind of the easy way to put it. But there are many things that are important to be taken into account. And the one thing that's important is that when you are scaling a blockchain, you also want to make sure that you keep the blockchain decentralized and secure. And the most difficult part here is decentralized, because one easy way to scale a blockchain is to ask for the nodes to be really, really big. And then they can make more computation, more transactions per second, and they also can maybe transfer more data over the network. But then this kind of start to centralize the blockchain. So what we want to do is to make sure that the throughput of the entire blockchain is much, much, much higher, but at the same time, we have the same small requirements for the nodes that are running on the network. So we started with a roadmap in 2018 that was focused on sharding, and this changed in 2020, where we started this kind of roll-up centric approach, in which we had an idea to build a Bitcoin chain, but at the same time let other institutions to create roll-ups, some of them optimistic, some of them based on zero knowledge, and that would be the way we scale Ethereum. Now, the issue that comes with this is that rollups need a space. And so they need some place where they can put their proofs and everything that is required to make sure that the rollup is actually safe and fair. So they kind of inherit the security of the layer one, but they need to put their data somewhere. So that takes us to DNEP Cancun, which was the hard fork that happened a year ago, more or less. And so before that, what we had in Ethereum was this thing that we call cold data, where you could use to put data into the Ethereum blockchain. Okay, you can put anything there. You can put a poem, you can put roll-up transactions, proofs, whatever you want. Now, the issue with cold data is that the data that you put there is there forever. Okay, you can never remove it, and so that's kind of a really bad thing. That's a long-term commitment. It's forever, you know, and so that's not good. The other thing is that's a very limited space. You can only store a couple of megabytes. I think the largest blocks that we have seen in Ethereum are about 2 megabytes. So this is limited in space, and it's also very expensive in terms of storage. I think we have to pay about 16 gas per byte, except if it's a zero. But so the thing is that is forever, is limited in space, and then it's also expensive. So that's not great. So to solve that problem, we invented Tinder, or what we actually call blobs, but it's more or less the Tinder of Ethereum, because it solves these three problems. So if you don't like these long-term commitments, you have this other solution where you store data and it's only stored for 18 days, and after that you don't have to see it again. You know, it's gone forever. You don't need to care about it, right? So that's good, and it's also a little bit larger in terms of space, because you can scale blobs. You can grow the number of blobs, Every blob is about 128 kilobytes, and then if you increase the number of blobs, then you will have more and more space. We expect to have tens of megabytes soon, and perhaps even hundreds of megabytes of blob space in every slot soon. So that also gives us much more space to store all the proof and things that L2s require. And the other aspect that is interesting is that it's not that expensive because it's a different, an independent market, right? And so that kind of solved all these three problems that we had with cold data, okay? So we introduced blobs in DNAP, and this is a distribution of how many blobs per block we observed last year. This was at the time of DEF CON in Bangkok. And so you see here, the blue color is 0 blobs, and then the pink one is 6 blobs. And you see more or less what is the distribution of blobs per slot that we had at the time. The maximum at the time was 6, and the target was 3 blobs per slot. And a slot is 12 seconds, so every 12 seconds we are producing between 3 and 6 blobs. And then what you see on the other figure is the latency of propagation of those blobs over the network. Latency propagation is what's very important for us to study, because we need the blobs to arrive within the first 4 seconds of the slot to make sure that all the nodes in the network see the blobs, and they can be sure that the block and the blobs are available. Okay, so once they are sure that the blobs are available, they can say, okay, this is a valid block, and I can validate it. Okay, so this needs to happen quickly, and so increasing the number of blobs poses a risk, because that means that you will take more and more and more time to propagate this data over the network, and then probably some nodes will receive them a little bit late, and then will validate the block a little bit late. So this is something that is important to take into account, and then we study during the time we started blobs in DNAP, and actually even before we started studying that. So today we have Pectra, and we changed the limit of the number of blobs. So before it was 3, the target was 3 and the maximum was 6. Today, the target is 6, and the maximum is 9. Okay, so we are scaling the number of blobs, so that means the amount of data that you can put in every slot. And so what you see in this figure is more or less the distribution. So in blue, you have before Pectra, the Pectra fork, and then in yellow is after Pectra fork. So we see that now there is like slots with 7, 8, and 9 blobs. Okay. Now, what we expect to have for the next fork, Fusaka, we expect to have PRDAS. PRDAS is basically data sharding. That means that the nodes in the network don't need to have all the blobs all the time. Instead, what they do is they take only a specific number of columns. So imagine these blue rectangles that you see here are the blobs. So you have, in this case, for example, 4 blobs. And what happens is that the nodes in the network will only download a number of columns, but they don't have to download the entire blob, okay? And this is the way we scale blobs. Like, we can allow more blobs and more blobs, because you don't need to store all of that in your node, okay? So that's what we call data sharding. We are sharding the data, and then you only need to store a couple of columns, and everybody store a couple of columns, and then the replication is high enough to make sure that every column is replicated enough times, and you are sure that the data is actually available. But then you need to do sampling to make sure that the data is available, but I'm not gonna get into the details because I want to present something different today. Okay, but then basically the idea is the following. First thing you have to do is to disseminate your blobs over the dev peer-to-peer network. The execution layer client has to download the blobs, and then they can extend it through erasure coding. The consensus layer nodes have to verify the availability of the blobs by downloading the columns that they have to custody, and they disseminate also these columns through the gossip subnetwork. Okay. And then at this point, every consensus layer node has to custody a minimum of 4 columns, but you are also allowed to custody more if you want. For example, if you want, you could download all the columns, okay? And this could be useful for specific nodes, for example, nodes that are running block explorers, or they are a node that is running with hundreds of validators in one node, that, and is, it has to be producing blocks quite frequently. It's good to have all the columns to make sure that the chain is correct and your head is correct. So what are we proposing for Glamsterdam? So today what we have is a one-dimensional erasure coding. So we extend the data only horizontally. But the idea is at some point to move to this pattern in which we extend the data in 2 dimensions, horizontally and vertically. Okay? So what you see in this figure is the blue square is basically the blob data. Each row on that on the top left for you, on the top left, each row is a blob. Okay? And then you have a number of blobs that you put one under the other. Okay? You create this matrix. You erasure code this matrix. You generate the red square that is on the side, and then you erasure code that with Reed-Solomon, and then you generate the bottom part of the figure. Okay, and so this is a 2-dimensional erasure coding scheme that allows us to sample the validity and the availability of the data much more faster. Okay. And then we have to disseminate rows and columns over the peer-to-peer network. So this is the plan that we have for full scaling in a couple of years, and this is the target. Okay, so today I was talking in the previous in Fusaka, we only have to download columns. The idea is that at some point we will have to download a number of columns and a number of rows. Okay. So what I'm proposing in this presentation, this research, is to have Ethereum sharding. So I explained that in Fusaka, we will have data sharding. We only, instead of downloading all the blobs, we only download a couple of columns, right? And so we avoid the fact that we have to download all the blobs. But this is a little bit naive in the sense that, okay, you have data sharding on the consensus layer client, but on the execution layer client, you are downloading all the blobs in order to produce blocks. Okay, so it's kind of naive. You are doing data sharding on the consensus layer, but in the execution layer, you are not doing data sharding. So that's not very clever. And so we understand that at some point, we are going to have to shard the blob mempool as well. And so one of the ideas that we are proposing here is to do this sharding based on the transaction hash. Okay, so in every node you have a node ID, and then what you can do is take the transaction hash and look at just the last byte or the last half byte of that transaction hash, and if it matches with the last half byte of your node ID, then you download that transaction and you download all the blobs related to that transaction. Okay, if it's not the case, then you don't download it. Okay, as you can see in this figure. And so this is something that we can actually start implementing today. We don't even need to do a hard fork for this. We can actually start trying it today. So, but there are other ways to do this, the sharding. One of the ways to do, instead of using transaction hash, you could shard it by the transaction sender. Okay, so instead of looking at the transaction hash, I look at who is sending me the transaction, and if the last half byte of that address matches my node ID, then I will download that transaction, type 2 transaction. So we tried this. We looked at all the type 2 transactions for about 3 weeks. So it was about over 6,000 epochs, more than 700,000 blobs. And what we noticed is that the distribution using the transaction sender is not really good. It's actually very non-homogeneous. And the fact that this happens is because there are actually rollups that are very very heavy in terms of using blobs, and those are the ones that are sending a bunch of transactions. So that's what you see, the big column that you see there is probably base, who is sending blobs all the time, and so you don't have an homogeneous distribution there. Then we try to apply the hash of the transaction sender address. It improved a little bit, but not much. So that wasn't great. So we're still experimenting. One of the things that, as I proposed, one of the things that we evaluated was how this distribution looks like when we do it with the transaction hash. And now what you see here is basically the distribution of nodes in the network. So today we have about 8,000 plus nodes in the Ethereum network. And if you look at the node ID and the last half byte of the node ID, that is the distribution that you will observe, which is quite homogeneous there. And if you look at the types of transactions that I said previously, so that 250,000 plus transactions, and you look at the hash, and only the last half byte of the hash, you have a very homogeneous distribution. It's the same way if you look at blobs. Is because in one type of transaction you can have multiple blobs, but if you do the distribution, you get also a very homogeneous distribution. Now, we also look at, but yeah, so this is the total distribution over a period of time of 3 weeks. So we also look at how this distribution looks day per day, right? Because if it's a long time, maybe just one day is unbalanced and the other one is unbalanced in the other way, and they compensate each other. So we look at how this looks in a day-by-day basis. And what you see here is, so in the x-axis you have every day of this evaluation period. And the box plot that you see basically is, the bottom is the minimum of blobs in that particular chart, and the max is like how many transactions you had in that chart. And basically what we are trying to get here is that these columns are as small as possible, so that the difference between the min and the max is not too big, okay? So we did this analysis by 24 hours, then this is by 12-hour analysis, and this is 6-hour analysis. So you can see that more or less all of these periods had about 400 transactions, 400 blobs in the lapse of those 6 hours, and they are more or less kind of well distributed across all the 16 charts that we had. So you see that almost all the minimum are around 300, and the max probably around 600, and the kind of like the large amount of these periods are between 400 and 500 transactions per chart. Okay, so that's quite a fairly good distribution. Now, we already started implementing this in Geth and Reth. Yes, there is progress there, and hopefully we can start experimenting in DevNets quite soon. Now, to complement this, we need another part of the puzzle, which is partial column dissemination. So instead of sending full columns, as happens today with Fusaka, the idea is that in the future we can also send part of a column or even just single cells, and that will make things very easy, because what happens is that different nodes will have different blobs because they belong to different charts, but between all of them, if they send only their partial column or single cells, you can reconstruct the entire column as we have it today, okay? So these two things together can fit in a way that is quite efficient to decrease at the same time network bandwidth and reduce latency while sampling data on the network. So, and then we come back to this figure, which is what we have this vision of what full does is expected to be in a couple of years, where we can have the two-dimensional racial coding and the sampling in terms of columns and rows. So just to finish, okay, so there is a bunch of things that we can add or remove from this proposal, but I'm not gonna discuss them here. Maybe you can ask me for questions if you want. But yeah, overall, I think these two parts combined, having a sharded mempool and at the same time partial column dissemination, actually fit very well to shard the blob mempool, and at the same time improve latency for sampling at the consensus layer. And I think it reduces a lot of redundancy that we have in the peer-to-peer network today, and makes the system more scalable. So I think that's all I wanted to present for today. Thank you very much. Yes?
So doing the 2D ratio coding, that increases like the computation that you need to do. Have you done any work to like determine whether it's actually feasible to still do this within the 4-second time window that you have in order to propagate these?
Yes, so yeah, doing the two-dimensional racial coding increases a little bit the computation that is required to do this generation, but not dramatically. It doesn't bother too much the 4 seconds that I was presenting at the beginning of the talk, the time that you have to disseminate the thing. What happens is that at this point, the horizontal erasure coding happens in the execution layer. When you receive your blob, you validate that the blob is valid, you can already do the erasure coding or the extension horizontally, and you can do the vertical extension later after you receive the partial column dissemination. And so different players in the network can do the different extensions at different times, and is not part of the critical path, so for the 4 seconds time.
Actually, the propagation is for the full blob, but then what you end up keeping is a subset of that, the erasure coding generated.
Yes, that's correct, yes.
Thank you. We have to switch to the next talk.
Thank you very much.
much.